Picture this. It's Black Friday. Millions of people are furiously mashing refresh on their shopping carts on some massive e-commerce platform. And then, bam, a severe network partition strikes, and an entire data center just goes completely dark. Now, in the old days, this would mean a catastrophic system collapse, millions of dollars literally vanishing, a total PR nightmare. But today, for the best engineered platforms out there, the users don't even notice. The checkout process just keeps humming along like nothing happened. So how is that even possible? Well, welcome to this explainer. By the end of our time together today, you're going to know exactly how engineers design these unbreakable systems, and basically how they prevent the digital world from collapsing under pressure.
Okay, let's dive right into this. Here is our roadmap for today. First, we'll look at reliability versus availability. Second, the consistency trade-off. Third, building fault-tolerant systems. Fourth, achieving high availability. Fifth, the Amazon Dynamo model. And finally, designing for maintainability. Let's get to it.
So, to truly understand system design, we really need to start with a fundamental mindset shift. You've got to ask yourself, what happens when your servers inevitably die? Notice I said when, not if. We aren't designing systems that assume everything's just going to work perfectly all the time. In a massive infrastructure, we're talking millions of components. Hardware and software failure isn't some rare exception. It is the default state of operations. Designing for that exact reality is what separates the fragile systems from the truly unbreakable ones.
All right, Section 1, reliability versus availability. People use these terms interchangeably all the time, but they are actually very different. So the crucial point here is drawing a hard line between a system's ability to function correctly over time versus its overall accessibility. Let's break it down. Reliability is measured by mean time between failures, or MTBF. Basically, it asks, how long can this system run without making a mistake or throwing an unexpected error? Availability, on the other hand, is just uptime percentage. It's simply asking, is the system operational and responding to me right now? And here's the kicker. You can actually have a highly available system that isn't highly reliable. Take that famous 2017 cloud outage, for example. The services technically stayed online and accessible, sure, but critical functions completely broke down because of a mistyped command. So it was available, but entirely unreliable.
To really cement this idea, let's contrast two vastly different industries. Aviation software demands absolute, incredibly high reliability. A software failure mid-flight is literally life or death, right? There is zero room for error, so functional consistency is absolutely paramount. But on the flip side, consider an e-commerce platform. Here, high availability is king. If a product image glitches out or a review doesn't load right away, that's totally fine, as long as the user can still hit that buy button. The whole system just has to stay up, even if it's acting slightly imperfectly.
That tension between perfection and accessibility leads us perfectly into Section 2, the consistency trade-off.
This is basically the ultimate boss fight of distributed systems. Enter the CAP Theorem. It states that a distributed system can only guarantee 2 out of 3 specific properties at any given time. First, consistency. This means every single user sees the exact same, completely updated data no matter which node they connect to. Second, availability, meaning every request gets a response, no exceptions. And third, partition tolerance. The system keeps operating even if the network splits or nodes just stop talking to each other. Now here is the secret. Because network failures or partitions are completely unavoidable, cords get unplugged, routers crash, partition tolerance is non-negotiable. You have to have it. Therefore, when a network fails, you are fundamentally forced to choose. Do I maintain strict consistency or do I guarantee availability?
Let's look at how different industries actually make that choice. A CP architecture chooses consistency and partition tolerance. Think of a financial system. If a bank's network fails while you're trying to wire money, the bank is going to intentionally reject that transaction. It sacrifices availability to ensure your account balance remains strictly correct. Nobody wants magical money appearing or disappearing. An AP architecture, like a social media platform, chooses availability. If their network lags, they're going to happily show you slightly outdated posts or maybe delay your like count just to keep you scrolling. They embrace what's called eventual consistency to make sure the app is always responsive.
Knowing that faults are definitely going to happen, let's shift to Section 3, building fault-tolerant systems.
There's this great quote directly from the architects of Amazon's Dynamo system, and it really says it all. Treating failure handling as the normal case without impacting availability or performance. You see, fault tolerance is not about preventing failure.
That's literally impossible. It's about creating this invisible communication layer that intercepts and manages the failure behind the scenes, without the user ever noticing a drop in performance.
So how do engineers actually achieve that invisible management? Well, modern platforms use asynchronous communication and message brokers to break apart direct dependencies. Imagine a microservice system handling something complex, like federated learning. If a single message broker node goes offline, the whole system doesn't just halt. Because the interaction is asynchronous, the traffic is just dynamically redistributed among the remaining healthy components. By prioritizing fault isolation and decentralized state management, engineers make sure that a single broken component never, ever triggers a catastrophic system-wide collapse.
Which brings us to the mechanics of it all in Section 4, achieving high availability.
Look, high availability isn't magic. It is just really meticulous engineering. It relies on replication, basically creating redundant copies of your data across different locations so you never have a single point of failure. It uses automated failover mechanisms to instantly automatically switch to a backup if a primary server crashes. And then you have load balancers, acting like traffic cops, dynamically distributing millions of user requests across all the healthy servers. But honestly, perhaps the absolute most brilliant technique is this next concept.
Graceful degradation. It is such a smart concept. Instead of a server completely crashing under a massive load, it intentionally turns off non-essential features just to save the core business function. For example, let's go back to that massive traffic spike on Black Friday. An e-commerce site might temporarily turn off personalized product recommendations or hide the user reviews. Yeah, the site might look a little bare bones for a few minutes, but the shopping cart and the checkout process remain fully available. It sacrifices the nice-to-haves to save the whole shebang.
To see all of this in action together, let's dive into Section 5, the Amazon Dynamo model. Amazon built Dynamo for a very specific reason. Their shopping cart service needed to be always available, even if hard disks failed or entire data centers were wiped out. And this brilliantly illustrates how they did it. They used a concept called a consistent hashing ring. Data keys are partitioned and replicated across multiple nodes sitting on this ring. Because they structured it this way, if node B suddenly departs or crashes, it only affects its immediate neighbors on the ring. The rest of this massive network remains completely unaffected. It's like a localized quarantine.
Now, what's really interesting about this slide is how they took that ring and seriously optimized it using something called virtual nodes. Think about it. Physical servers have different capacities, right? Some are brand new and super fast, some are older. By assigning multiple virtual nodes to a single physical server based on how powerful it is, Dynamo can evenly disperse the request load. Better yet, if a physical server crashes, its virtual nodes just disappear, and the newly displaced load is smoothly absorbed by all the other available nodes in the entire system. It completely smooths out the shock and prevents those terrifying cascading failures.
But remember the CAP theorem we talked about? Because Dynamo strictly prioritizes an always writable experience, meaning they always want you to be able to add items to your cart, it sacrifices strict consistency. Instead, it embraces eventual consistency. Say there's a network partition. You might actually end up with two different versions of a shopping cart being updated at the exact same time. Well, Dynamo accepts both. It will never reject your write. Instead, it leaves the conflict resolution, merging those two conflicting carts, to automatic background processes to just figure out later. In the Dynamo model, availability always wins.
All right, wrapping things up, let's move to Section 6, designing for maintainability.
This is truly the unsung hero of system design, because eventually humans actually have to manage, fix, and upgrade these incredibly complex architectures. I mean, a highly available system is totally useless if it keeps your team a week to fix a minor bug. Maintainable systems do not happen by accident. They're built on accessibility, so physical or digital parts can actually be reached. They rely heavily on modularity. Think of a microservices architecture where one faulty module can be hot-swapped or updated without tearing down your entire infrastructure. They also embed rich diagnostics for early warnings, and they insist on strict standardization. That way, any engineer, anywhere, immediately understands the components they are looking at.
Let's move to the next slide and see how this builds into a complete design lifecycle. You definitely don't just bolt maintainability on at the very end. You start step 1 by defining your maintenance objectives and analyzing requirements. Then you actively incorporate it right into the design phase. Next, you actually test for it, literally simulating maintenance scenarios like hot swapping a server just to see how the system reacts. And finally, you monitor and refine post-deployment. Use telemetry and service level indicators to make sure your system can evolve safely over time. It's a continuous loop.
Which brings us to our final thought for this explainer.
The illusion of the perfect, unbreakable system is really just that. It's an illusion. Behind the scenes, servers crash, networks split, and errors are occurring literally every single second. The only difference is intentional design. So whether you are building a banking app or the next big social network, I want to leave you with this question. When your system inevitably breaks, what deliberate, engineered trade-offs have you designed it to make? Thanks for exploring this architectural balancing act with me today. Keep building resilient systems.